Let's have a look now at a somewhat more useful application of pointers. Okay, we went through this example where we were pretty much using a pointer as a different way to access a given variable. So we will see how this is useful, to, like I mentioned already, pass parameter by reference, allow local variable inside a function to access variables from over activation record. But in this video, we're going to focus on another application of pointers, which is actually support us when we are trying to dynamically allocate memory at runtime. So how do we dynamically allocate memory? There are several functions which allow to do this. Several functions for the standard C library. The one that we are going to illustrate in those videos is malloc, because it's kind of like the general purpose memory allocation function of the C library. The way that malloc works is malloc is going to take as parameter a size, an amount of bytes which you want to allocate in memory. So let's say you want 1024 bytes allocated. You would specify here the number of bytes you want. What malloc is going to return to you is the address of a newly allocated dynamical memory chunk, which is of size 1024 byte in this example, and which you can start using immediately. So this is where pointers enters the picture. Okay, what does it mean, start using it immediately? Well, it means that this chunk of memory has been found somewhere, so there is enough memory available, and it has been reserved for your usage, which means hopefully it's not going to be overwritten next time an activation record expands or things like that. So malloc is getting his memory not from the program execution stack. Okay, otherwise, like I already suggested, there would be problem with activation record overwriting this memory as we call new functions, etc. No, it takes its memory from another area of the program's memory space, which is the data segment. So far, okay, we have been mainly talking about the stack, okay, showing the activation record as the main, over activation record as we call functions, invoke them. Now here we are going to have data in the activation record as the main, PTR in the activation record as the main. But when we call malloc, malloc is going to locate a chunk of, let's say, 1024 bytes, okay, in this example, so that would be probably a little bigger than this, okay, to keep things semi to scale. So here's our chunk of 1024 bytes, and PTR is going to be assigned the return value of malloc, which is going to be the address at which this block of 1024 bytes starts. So let's call it alpha, okay, to keep things general. I'm going to call malloc. Malloc is going to find a chunk of memory big enough to accommodate my needs. It's going to lock it, reserve it for my usage, and then it's going to return to me the address where it starts. And then from there, I can actually start dereferencing PTR to write some data into that newly allocated chunk of memory. In the example, as it stands right now, it's not clear why I chose 1024 bytes. Okay, hard coding a value like that is generally a bad idea. PTR is supposed to be a pointer on int. So the thing that would make most sense is to say I want to allocate enough memory to store one integer. Okay, so I know on my system it's going to be 4 bytes. So I could write things like that. But the problem is portability. If I compile and run this program on another platform, say a 64-bit platform which encodes its integers on 8 byte, that's going to be a problem. I'm not allocating enough memory. So instead of providing a hard-coded value like this that corresponds to the internals of my platform, I'm going to use a size of operator, which is going to allow me to say I want to allocate exactly the number of bytes which is used to store a variable of type int. So I don't have to worry anymore about how many bytes exactly int is spanning. Okay, I just say malloc for me, memory allocation of size of int byte. And then I can use it like this. I can dereference PTR. So let's update a little the stack diagram here. Instead of a large chunk of 1024 bytes, I'm going to have here just 4 bytes, just enough allocated for me to store one integer. the address at which this block of 4 bytes starts, I'm still going to call it alpha. Okay, PTR points to this block, and when I do start PTR, I dereference to the address contained inside PTR, okay, which is alpha. So I go at address alpha. Because PTR is a pointer on int, I know that I'm manipulating the 4 bytes starting at address alpha, and I'm manipulating them using a binary encoding, which is a binary encoding of an integer. So I write the number 999 encoded as an integer, spanning the 4 bytes located at starting at address alpha. This is exactly what this little program here is doing. Okay, so just to complete this this little demonstration, let's add a little printf here. Printf start PTR is, and I'm going to display the integer value located at address start PTR. Okay, so I'm going to display it before I assigned it, so right after the allocation, and after. Let's save, compile, run. Before, this is what the memory, this is what the 4 bytes at memory address alpha contain when decoded as an integer. After my assignment, this is what they contain. So first thing to notice, do not assume that when you allocate dynamically memory, do not assume that there's anything meaningful in that dynamically allocated memory. Malloc is not going to set every one of the bits of your newly allocated chunk to 0. It's not going to do anything. What is in those bits is what was there before. Okay, so the last time that you did a malloc, maybe you had this segment, okay, you encoded something into it, then you released it, and now you allocate it again, and you find the previous value still lingering in memory. So do not assume anything being initialized for you in terms of what's inside dynamically allocated memory. Okay, first lesson. Second lesson, well, we are writing here inside of this memory address star PTR the value 999. This is going to persist for the lifetime of the program. So no matter what I do in terms of calling functions, okay, no matter what I do with over local variable, you see clearly that this is here stored separately on the data segment, and it's going to stay until the end of the program or until I deallocate it. So this is how I would deallocate this memory, this dynamically allocated memory chunk, okay? Free, which is another of the basic dynamical memory allocation function of the standard C library, free, and then an argument here which evaluates into a memory address. So in this case, the expression is easy, that's just PTR. PTR contains the memory address alpha. So I'm telling to the free function to pretty much stop blocking the memory, the 4 bytes at memory address alpha for my usage. Stop reserving them for my usage. Very important to understand what free doesn't do. Free does not modify what is inside of PTR. So PTR still contains the address alpha. Free does not override the bits, the 4 bytes worth of bits at address alpha with zeros. The value 999 is still located here at address alpha. Really? The only thing that free is doing for us is telling pretty much a runtime system that this piece of memory that was reserved, dynamically allocated for us to be used in our program, is now available for another memory allocation, for example. So it's really important to understand exactly what free does and exactly what it doesn't do for us.